So hi again. In this video we're going to talk about another search algorithm, and it's called binary sort. Now binary sort is an extremely efficient search algorithm. The basic idea of binary search is that if you have a sorted array and you look in the middle and you're looking for something, you know whether the element you're looking for is in the first half or the second half because it's sorted. Let's say you have an array of integers and the middle element is 5 and it's sorted in ascending order. So if when you're looking for 7, you'll only look at the second half. Basically what you do is you look in the middle of an array and then choose one of the halves, and then take that half, look in the middle again, choose one of the halves, and so on, basically until you find what you're looking for. Now let me explain that with an example array. So we have this array 1, 12, 56, 78, 92. It meets the prerequisite for binary search. It's sorted. So we look into the middle element and we find out that it's 56. Let's say we are looking for 78. So we can effectively ignore 1 and 12, and so even if we don't delete 1 and 12, effectively we're now only searching this. We're searching 56, 78 and 92. Now we look in the middle and we find 78 and we've found the element. So the algorithm has done its job. Now since we only had an array of 5 elements, it's done it in 2 steps, or else it'll obviously take a much longer time. Now I want to highlight a few things about binary sort. One is that in the scenario of an even numbered array, let's say we have a sorted array 3, 6, 9, 12, 15, 18, which clearly has an even number of numbers, we don't have a proper well-defined and demarcated half, because we have a third element and the fourth element that can be, which are like almost halves, but we don't have an exact half. So what we do for the purposes of this algorithm, we can just arbitrarily choose either the left part or the right part. It's not going to make a difference, because regardless of what we choose, we're going to discard the other parts only if we don't need them. And another thing I want to highlight is that we may include or exclude the middle element. I mean, there's no gross violation in excluding the middle element if you know that what you're looking for is not there, right? Because you know it's not there. Why do you want to include it? You can exclude it if you want. For our purposes, when we implement binary search in a few minutes, we are arbitrarily going to choose the left half if there's an even number element array, and we are going to exclude the middle element. And one more thing I want to highlight is that, what was it? I wanted to highlight something else. Just give me a second. One more thing I wanted to highlight was that whenever we do this, we have to keep track of the first, last and middle variables, because this is actually part of a bigger array. We have to see which addresses we are searching, so we have to keep track of the first index, the last index and the middle index. So now let's go ahead and implement the algorithm. So for our algorithm, basic things that we need are the variables to store the first, last and middle indexes. And what we need to do is we need to repeatedly compare the search element to the middle of the array we are searching, then update the last, middle or first accordingly. So let's say we have once again this same array 1, 12, 56, 78, 92, and we're looking for 78 once again. So what happens is, like, at first let's say this is the whole array. So at first our first variable will hold the index of the first number, which is 0, and last will hold the index of the last variable, which is the fifth variable. So basically the index is 4, and we calculate mid by computing the average of the two, that is first plus last divided by 2, which in this case turns out to be 2. So the index of the middle element is 2, which means that it is 56, because the index is this, 1 is 0, index of 12 is 1, index of 2 is 56. So yeah, so we need to repeatedly update first, last, and mid, and obviously we need a loop because we need to keep halving and halving. Now let me I've already written down the code because it's actually difficult for me to write down the code and explain at the same time because the algorithm is pretty complicated. So I've written down the code. I'm going to run you through it and yeah, guide you. So we begin with an include IOStream, which if you're using Turbo C++ should be include IOStream.h, and using namespace std is something you should ignore if you're using Turbo C++. It's just a syntactical requirement. So we begin our main function int main. So the first thing that we do is create an array of an arbitrary size 50. Then we ask the user how many elements they want to enter. We say enter desired array size. Then we declare an int size and take in the value of size from the user. Now we want to know what the user wants to search for. So we say enter search element, we declare int search and take it in. That's what the user wants to look for. And since the user wants a size number of variables, we have to allow him to enter it first. So int so we use a for loop for that. For int I is equal to 0, I is smaller than size plus plus I, cout enter element I plus 1 to account for the discrepancy. Discrepancy we start counting from 1, computer start counting from 0, and we say cin array1 I, where array1 is the name of the array we've declared there. So now so we take in basically every element that the user wants to enter from the user. Now we as we said, we need to declare declare the elements first, last, and mid. So if we have an array 1 2 5 okay 1 2 6 7 13, it's sorted, so that works. So first will be 0, last in a general case will be size -1 because the user wants the thing to be sized. The user wants the size, the number of elements to be sized. If the number of elements is size, the index of the last one will be size -1 because computers start counting from 0. Now and then we declare int mid. So it goes inside this while loop, and the test condition I'll explain soon. So basically what we want to do is we want to, let's go back to our 1 2 6 7 13 example. What we want to do initially is we have a value for first and last. So what we want to do first is give a value for mid. So for this array, first will be 0, first will be 0, last will be 4, and mid should be the average of the two. So initially we give mid a value of 2, and let's say we're looking for the element 2 in this array. So we compare the second element, that is the midth element, with the search element. When the search element is 2, so the middle element is 6. We're looking for 2. So what we do is, since we want to ignore it along with the first element, basically where we want to somehow be able to ignore 6 7 and 13. So what we want to do, we want to basically make our last element 2. So initially it was 1 2 6 7 13, so 2 comes before the middle element obviously. So what we want to do basically is make last equal to mid -1 because it's in the left half, so we just want to ignore this. And if we're looking for 7 and not 2, what we want to do is basically ignore 1 2 and 6. That is, we want to make first be equal to mid +1 and let last remain the same, right? And Yeah, so that's what we do, and then after that we rerun the loop and basically find the element at one point of time. So we have this loop here, mid is equal to first plus last divided by 2 if search is larger than array mid, that is if the search element is present in the second half 1 4 5 7 8 9. If the element is found in the second half, then first should become mid plus 1, right? Because 1 for 7 ignored, search becomes the one after 7. First is equal to mid plus 1. And if search is smaller than array 1 mid, then we basically want to ignore, if it's smaller than the middle element, basically want to ignore 7 8 and 9. So last becomes mid minus 1. And if search is equal to array mid, then we say search element found, just search element found. We don't care about where it's found and how many times it's found and all. And so we break out of the loop. And notice that when we keep running through the loop, it'll either keep halving or it'll somehow find it in the middle and then it'll somehow find it in the middle and terminate the loop. So I'm trying to imply that if you're looking for an element and it's present, it'll at some point of time it has to be in the middle. So let's see an example of 1 for 6. Even initially, let's say we're looking for 6, it's not in the middle, but after we ignore 1 and 6, it'll be in the middle. That is, eventually after a certain point of time, we'll only have one element left, and that one element will, in the worst case scenario, we'll have one element left. In that one element will be the first, mid and last. So if search is equal to array mid, and so it'll be found eventually. If it's present, it'll become the middle element, the first element and the last element. So it'll be found by this else if clause. Okay, now so basically we have an array, we have the what goes inside the loop. Now we want to see what's the test condition. And I claim that the conditional statement is first is smaller than or equal to last. That is, as long as last is not smaller than first, the loop keeps running. So if last is smaller than first, loop stops. Why does that make sense? Well, let me explain. So let's say we have an array of 1 2 5 7 8. First will be 0, last will be 4, and from that we compute mid, which is 2. Let's say we're looking for 9. So it goes to the middle element. 9 is larger than 5, so it ignores 1 2 and 5, and now we have the element 1 7 and 8. And since our initial thing was 1 2 5, and 7 becomes mid plus 1, that is 7 now, first becomes mid plus 1, first now becomes 3, because our first element is now essentially 7. So first becomes 3 and last becomes 4. And of course, when we do that, we have to recompute mid, and we recompute mid, we find the average of the two, which is 3.5, but for C++ that is basically 3, because mid is an integer. So what we're doing is we're arbitrarily choosing the left, because of the way C++ ignores the part after the decimal point. It'll go to the previous integer, that is, it'll go to the left part. So mid is basically 7 now. Now we're looking for 9. 9 is larger than 7, so what it does is it ignores the middle element and everything to the left of it. There's nothing to the left of the middle element, so it just ignores the middle element. And also it updates first to the value of 4, like I said. Yeah, so eventually you'll end up with one element, and mid we recompute, mid is also 4. So now we have reached a state where we only have one element left. First, last and mid are the same. Now we look in the middle again, which is just 8. We realize that 9 is larger than 8. So what the algorithm says is basically what you do every time the search element is larger than the middle element. If search is larger than array 1 mid, first simply becomes mid plus 1. So basically what will happen is first will get incremented to the value 5. So basically what's happened, and last won't change because that's what our algorithm says. Mid is equal to 4, last is equal to 4, first is equal to 5. So basically what has happened is first has become larger than last. Now for us that doesn't really make sense. How can first be larger than last? But for the computer, all first and last are simple integers. So when we reach a stage where first is larger than last, that means that we have searched every element that we can possibly search and we haven't found it. So if such a scenario happens, what we do is we break the loop. That is, if first is larger than last, we break the loop like I've written here. So as long as first is smaller than or equal to last, the loop keeps running, which is why a conditional statement is while first is smaller than or equal to last, blah blah blah. Okay, so I hope that makes sense now. So yes, so now all we have is we close the while loop and return 0, and this should work. I'll just let me just check if all the comments are enclosed properly so that we can go ahead and run this program. Yep, they're all proper, so let's run it. Control F5. Yes, I want to compile it. Now see, we know that the array has to be sorted, but for our program we haven't actually specified a sort algorithm to sort the array in case the user enters an unsorted array. So basically what we're doing is we're taking for granted that the user enters a sorted array. So since we're the user in this case, we're just going to enter a sorted array to help ourselves out. Desired array size would be 5. Search element, let's say we're looking for 7, and element 1 should be 1, element 2 is 3, element 3 is 5, element 4 is 7, so it should find it, and element 5 is 9. So in an array, sorted array 1 3 5 7 9, the program has to find 7. So what it should do initially is it should go to the middle, which is 5 right here, and then it realizes 7 is larger, ignores 1 3 and 5, 7 and 9. It goes to the middle, it arbitrarily chooses the one to the left, so it chooses 7, finds it, terminate, and reports that it's been found. Do we have a cout statement to report that it's been found? Well, we'll find out soon. So let's see if it works. Okay, so we did include a cout statement. Search element found. So now we know that binary search works. Thank you. See you next time.